the chain rule. And here we are now with our last derivative property. And the chain rule is enormously useful. The chain rule will probably be in 95% of all the problems going forward at this point. And the chain rule is deceptively simple looking. And there it is. And if you look here, if you treat these as fractions, you can see these du's cancel, and you're just left with df over dx. So pretty simple looking, maybe deceptively simple looking, because it is enormously powerful and useful. And before we get to the chain rule, I just want to reiterate where we're at right now. So we have, for addition and subtraction, derivatives distribute. So if you have the operators of addition or subtraction, then you know how to deal with that when taking a derivative. The derivative distributes, and you can just take the derivative of each term individually. And now what we learned in the last lecture is for multiplication, if we want to take the derivative of two things being multiplied, two functions, then we have to use the product rule. And we also found from the last lecture that if you're going to take the derivative of two functions with division, then we have the quotient rule. So you might be asking yourself, well, what's left? If we have addition and subtraction, the derivative distributes. We have multiplication, we use product. If we have division, we use quotient. What else is left that the chain rule would apply to? And that answer is the fifth operation in algebra, which is the composite. For composites is where you use the chain rule. So I want to just do a quick little background here on composites. And the first thing I want to do is try this new shortcut. Let me see, Control Enter. Look at that, brings me to a new page. Look at this function here. What functions do you see here in this h of x? Well, the first function, the very first function you see. In other words, when you read this left to right, the first thing you're going to encounter is this parentheses. And this parentheses means something squared. So the first thing, the outer function here that I like to call, is a power function. The parentheses squared means a power function. And then what's inside that power function is the log function. And if you recall back to algebra, the composite, F composite G, means you take G and plug it into F. So if we take G, which is log x, and plug it into x squared, we then get log x squared, which is then our function. So what functions do you see here? You see a power function and a log function. And again, you should identify these things so you know which derivative patterns to use. So to do this derivative, we would need a power function and a log. So how about this one? What functions do you see here? Well, we have an exponential function, e to the x, and we have the power function 2 to the x. So 2 to the x is being inserted into e to the x. And I just want to make this statement real quick. Recall that the derivative of 2 to the x, constants we can pull outside the derivative. And so 2 to the x, I would still consider to be a power function. It's a power function times 2. But constants we can just pull out. Constants are real easy to deal with. Just pull it outside the derivative. So if I wrote this then as composites, this is what we would have. We would have the outer function. Again, when you read h of x, the first thing you're going to say is e raised to the 2x. E is the outer function here, e to the x. The inner function is 2 to the x. And so this composite, f composite g, means we're taking g and putting it into f. And that's how we then get e to the 2x. We're putting a power function into the exponential function. So what about this one? What functions do you see here? Well, there's an exponential function e to the x and a constant function of -1. We are putting -1, we are putting this constant function into the exponential function. And again, this is the composite from algebra. And so if I would write this out, I would write out, oops, I used f twice here. Let's call that h real fast. So our outer function, the exponential, the inner function is just the constant function -1. And so our h here is ultimately f composite g. We're putting g into f, and then that's how we get e to the -x. E to the -x is a composite function. So what about this one? What functions do you see here? So we have the trig function, sine. Then we have two power functions. We have 4x cubed as a power function, minus 2x as a power function. And then we have 5, which is a constant function. So to do this derivative, we will need the sine pattern, the power pattern, and the constant pattern to do that derivative. Now we're not there yet. I'm just showing you how to identify these things. And I again call this function f because it's so hard to break that habit. Let me call that h again. And so if I would demonstrate this composite function, I would say the outer function, which is sine, the outer function is the function you'll encounter first as you read this left to right. So the outer function here is sine. The inner function is the 4x cubed minus 2x plus 5. And then we can obtain h by doing f composite g. We put g into f to get this function. I have an extra x right there. Let me just get rid of that. And that's our composite function. So, very important here that you can identify these things. And there was a picture I wanted to show on the right here that I forgot to do. Let me just scroll up really fast back to the first one here, this one. What functions do you see here? You see a log function going into a power function. And again, I like to use objects to try to demonstrate this. if we say f is a square, and if we say the log is a circle, then this is just like putting a circle into a square. So log x is our circle. The power function is the square. We're now putting the circle inside the square. That's what composites do. So let's start with a straightforward example. Here is the chain rule here. I'm just going to have it sitting there on the right. And here is our function we're going to test out. And what functions do you see? So you see there's a sine function and there's a power function. The power function is inside the sine function. So if you look at the printout I have of all the derivative patterns and stuff, what you'll find on there is the derivative of sine is cosine. But that's not what we have here. We have sine of x squared, where the derivative pattern is just sine of x. So we can't just use the derivative pattern here because it's not the same. Sine of x squared is absolutely different than sine of x. But you know what would be nice here is what if we just said, let's just say u, I'm just going to introduce a new variable here. Let's just say u is x squared. We're just going to define u to be x squared. And if we do that, we can then change our function. Instead of this being x squared, this is just u. And now we have a function of u. And notice, if we write it like this, now it is in the form of the derivative pattern. Remember, this doesn't have to always be an x here. This doesn't have to be sine x. It could be sine t, could be sine w, it could be sine u. So we know this derivative right here from the derivative patterns. This derivative, the derivative of sine u with respect to u, so I have to change this x here to a u. The derivative of sine u is cosine u. We know that from our derivative patterns. So also notice, looking over at our chain rule to the right here, notice I have df du equals cosine u. And in the chain rule, you can see there is a df du right here. So we're actually, just by doing this substitution, we're halfway done with the chain rule. And the chain rule says, well, now that you've figured out df du, you have to multiply this by du dx. Now that means the derivative of u with respect to x. Well, here is u equals x squared, and now they're asking us, well, what is the derivative of u with respect to x? Well, the derivative of x squared is 2x. And so then the chain rule is saying, well, now you're done. Just put those pieces together. So we have, looking at the chain rule here, we want the derivative of the function with respect to x. The chain rule is saying that derivative of f with respect to x equals df over du, which we just figured out is cosine u. And then it says times du dx. And du dx, we figured out, is 2x. Now, the only problem with this expression is the u. We don't want the u in the long run. The u is just a helpful tool, and now we will get rid of this tool because we know u is x squared. Whoops. And that's our answer. That is the derivative. So here is our function, and here is the derivative. So what happened here? Well, we started with our original function, and we looked at it, and you said, or I said it at least, that, it'd be real nice if this wasn't x squared, because our derivative pattern is just sine of x. And wouldn't it be nice if we could just rewrite this without the x squared? And that was what I did then with the u. I just said, you know what? Instead of x squared, let's just call that u. And if we do that, we can then write the sine function in the form of the derivative pattern, which means we now have that derivative. But when we make this u substitution, the chain rule says, well, you have to use that u to also take the derivative and multiply your answer. And what I'm showing you right here is the common way to show the chain rule. Your math book will show it this way with the u as well. But I find in practice that almost nobody does this because it's very cumbersome, time-consuming, and especially as problems get harder, this can get very cluttered and clunky, having all this substitution everywhere. So I want to show you the way that I'm hoping you'll learn how to do the chain rule. And I want to start with x squared. So here is x squared. And what I want you to understand is I'm going to introduce this new word called argument. And this x squared, this is a power function, and its argument is x. The argument is what you put into the function. So this is a power function, and what are we putting into it? We're putting x into it, and so we call that the argument. Now you may be thinking, well, isn't that called the variable or the input? It is, but compare that to this next example. Here is another power function. Now we have a power function inside a power function. And we would say this is a power function with an argument of 5x cubed plus 4. The argument is the entire expression that you're putting into the function. Oh, and I have that written down here. The argument is the entire expression that's being inserted into the function. In this case, that's a power function. Let's try another example. Sine of x. This is a sine function with an argument of x. The only thing going in the sine function is x. That's it. There's nothing else going in there but x. Now compare that to this example. Now we have sine of log x minus 5x plus 1. This is again a sine function, but now the argument is log x minus 5x plus 1. The argument is the entire expression that goes into the outer function here. And so we would say what I have in blue here, this is the argument of the sine function. This is what's going into it. Let's check out another example. Log x. This is a log function with an argument of x. The only thing going in the log function is x. That's it. And now compare that to this example. This is, again, a log function, but now the argument is e to the x times sine x. E to the x times sine x, that's what we're putting into the log function. And so we would call this the argument. Now, just to be clear, this is the argument. The x is the input. So the x is the input here, the variable. But this entire thing going into the log function, we call the argument. So what's the deal with this argument thing? Well, if we go back to the chain rule on the right here, this df du, this is what I call the normal derivative. I put normal in quotes because you'll find when calculus 3 there actually is something called the normal derivative. So I don't mean that here. So I do have to kind of put that in quotes, but that's how I'm going to refer to this for our semester, is I like to call this the normal derivative. And what I mean by that is df du is the straight derivative you get from the derivative patterns. And I will show you examples, but this df du, that's just straight up the derivative pattern from the sheet that I had in last lecture. And then this du dx, that is the derivative of the argument. So df du is the outer function, and you just take that derivative normally, right from the patterns. And then du dx is the inner function, and then you have to take that derivative and multiply it by the normal derivative. And I'm going to show you that right now. And let me get my example here. Here's our function. Now the outer function is the one that you see first when reading left to right. So as you read this left to right, the first thing you're going to see is sine. Sine is the outer function. And then the argument is the inner function. So 4x squared minus 2x plus 1 is the argument of sine. And so in the real world, how is this derivative done then? Without all those u's and substitutions and stuff? Well, it's done with what I have over here written. Is the chain rule, and this is always true, the chain rule says, first, take the derivative like you normally would. So in other words, the normal derivative of sine is cosine. And that's just straight up from the derivative patterns. Now we're not done, but just straight up. If we just blindly did the derivative patterns, the derivative of sine is cosine. And that's what I mean by the normal derivative here. It's just straight up that derivative that's in the derivative patterns sheet. And there it is. The derivative of sine is cosine. But the chain rule says you have to multiply this by the derivative of the argument. And here is the argument. And a chain rule says we have to multiply by that derivative. And so what's the derivative of the argument? Well, that derivative then is 8x minus 2. And that is our answer. That is the derivative. So, let's try another one. How about the natural log of tangent x? Now again, the first thing you want to identify are what functions do you see? You see a log function, so we're going to need that derivative pattern, and we see the tangent function, and we're going to need that derivative pattern. So let's look then at how we would do this with the chain rule. Now the first thing we're going to do is the next thing we should do after identifying what we have is what are the inner and outer functions. The outer function is the first one you will read first. So when you read this, you say natural log of tangent x. Natural log is the outer function, tangent is the inner. The tangent is the argument of the log. So the chain rule says df du, that means take the derivative just like you normally would, straight from the derivative patterns. And what is the derivative of log? Well, the derivative of log is 1 over x, but we don't have x here, we have tangent x. And so the straight up derivative, the normal derivative right from the derivative patterns for log is just 1 over the argument, 1 over tangent x. Again, that's just straight doing the log derivative right from the derivative patterns. And the chain rule says, okay, now that you've done the straight derivative pattern, you need to multiply that by the derivative of the argument. And the argument is tangent x, and the derivative of tangent x is secant squared. And that's our answer. Let's try another one. What do you see here? Hopefully you see a power function inside a power function. So the first thing we do is we take the derivative normally. That's the df du part. And, let me backtrack a second here. Oops. Let me just make this clear. This is what I'm saying by df du, the normal derivative. What we're saying here is all of this we're going to call u. So if I would write all this out again, which I'm going to do now, just to show you the logic here, is we're going to define u to be the inner function. We're going to define u to be the argument. And when we do that, then we have a straight, simple power pattern. And that's what df du is. df du is always the straight up derivative pattern on that sheet. And you know the derivative of u to the 10th. It's 10u to the 9th. So you know this derivative it's 10u to the 9. That's just a straight up derivative right from the derivative patterns. And I'm just going to change this x to a u really fast to be consistent. And that's what I mean. Well, that is what df du means. It's just a straight derivative pattern right from that sheet. And there it is. But we don't want the derivative with respect to u. We ultimately want df dx. So df du is just one factor. So if we want the actual derivative with respect to x, the chain rule is saying, okay, you have your df du, and now you multiply by the derivative of u with respect to x. And that's what we have right here. That's this expression. Here's u, and du dx is saying, take this derivative now with respect to x. And we can do that. So the 7 will drop down and hit the 5 to make that a 35. And we subtract 1 from the 7 to make that a 6. And then the next term, the 4 drops down and hits the 3. So 4 times 3 is 12. And we subtract 1 from 4 to make that a 3. And in minus 2x, the derivative of x is 1. And so that's minus 2. And that's our derivative of u. And it's this that we multiply then by the straight derivative pattern. That is the du dx. And then to get our final answer, we would get rid of the u and plug back in what u is. And that's our derivative. That's going through all the steps again. But let me show you that again without the steps. Here's our function. We're going to take the derivative. The chain rule says, take the derivative like you normally would. So that means this 10 will drop down, and then we subtract 1 from the exponent. And there it is. That is df du. And then we multiply that by the derivative of the argument. Here is the argument. And now we multiply this by that derivative. And that's 35 then. And there's our answer. Now, is this answer the same as previous? It is. But if you can brain power this out more, if you can understand what the chain rule means, these pieces, you can directly go to the answer versus writing all these steps out. And in the real world, this is how most people do the chain rule. Because as problems get harder, going through all these steps can get very cumbersome. And so I want you to understand the simplicity of the chain rule. Now, again, I'm not saying that means calculus is simple. I'm not saying that. I'm saying there is a simplicity here, though, on how to apply this. And that's what I'm trying to show you here. The simplicity here is that you take the derivative df du. You take the derivative as you normally would, straight from the derivative patterns, and then you multiply that by the derivative of the argument. So let's try another one that has 2 chain rules in it. So to get this derivative, we will have to do the chain rule twice. So first off, what functions do you see here? You have a sine function. You have a log function and you have a power function. We're going to need those three derivatives. Now, what else do you see? What is, let me ask this. Let me just type this out. What is the argument of sine? What is the argument of the sine function? It's log of x squared. Let me ask you this then. Well, why is that so tiny? What is the argument of the log function? What's the argument of the log function? The argument of the log function is what's in the log function, and that's x squared. So let's check out this derivative. This is a double chain rule. So we'll use the chain rule twice. And the first thing we do is identify the outer function. The outer function is sine. And that's the first derivative we do. We just do the straight up normal derivative. And what's the derivative of sine? The derivative of sine is cosine. And so we're just going to straight up do that derivative like we normally would. And there it is. All I did was a derivative of sine. The derivative of sine is cosine. And now I'm going to be a little bit more thorough here. And I'm going to use this operator notation here because it can be very, very handy. So what we've done is we did the first step. We did df du. We took the derivative normally. And now the chain rule says multiply. So multiply by the derivative of the argument. And so there is my math statement. This math statement, 100% valid. Remember, the d dx is a command. It's saying, I command you to take this derivative. So let's do that. We'll keep going. So we did the first derivative. Sine is cosine. And now we need to do this next derivative. And notice again, this is a composite function. And that's why I asked you, what is the argument of the log function? Because now we have a new inner and outer. Now x squared is the inner function and log is the outer function. And so we're going to do the chain rule again. The chain rule says take the derivative of the outer function like you normally would. That's straight derivative pattern. And the derivative of log is 1 over x. So the derivative of log, natural log, is 1 over x. However, we don't have an x here, we have x squared. 1 over x squared is straight up the derivative of the log function. And that's what we did. We did the normal derivative. And now the chain rule says, great, I'm glad you did that, but you still have to multiply by the derivative of the argument. And so I'm going to write that out. We still need to multiply, there's my dot, the derivative of the argument. And the new argument now is x squared. And so there's our next statement. And now we can do that. Now notice x squared is our derivative pattern, which means there's no more chain rule. The chain rule stops once you get to the straight derivative patterns. So now we have, what's the derivative of x squared? Well, the derivative of x squared is 2x. And there's no more inner function, and so there's no more chain rule. And that is our final answer. And yeah, we could clean it up a little bit because those x's will divide out right there, but that's all we could do to clean that up. But that's our final answer. A double chain rule. Let's try another double chain rule. And I'm purposely choosing this one because of a common mistake that can happen here. So first, what functions do you see here? There's a sine function. Raised to the fifth means a power function. There's an exponential function with another power function inserted into it. So what you're seeing here is a sine, an exponent, and 2 power functions. There's 4 functions here. Now the part that's a common mistake is this next question. What is the outer function? So if you recall, I said the outer function is what you say first when you read this. And the way this is written, the first thing you're going to read is sine. And that's unfortunate because of this notation right here. This is very common to do, but you have to remember that this 5 technically means everything is to the 5th power. And so I ask you again, what is the outer function? The outer function is a power. The first, as you read this left to right, the first thing you encounter is the parentheses, indicating this is all raised to the 5th. So a little bit deceptive because of this shorthand notation by putting the 5 there. Very common though. I would be a bad teacher to ignore that. Very common to put a 5 there to indicate to the 5th power. And then you have to remember what that technically means. Because that technically means the power function is the outer function. So let's do this derivative. We do the outer function first. And we do that straight up. The normal derivative. Just do the regular old derivative. So if you had x to the 5th, you know that derivative is 5x to the 4th. That's what I mean by the straight up derivative. But instead of x, we have sine of e to the 3x. So again, that's what I mean by the straight up derivative pattern. Just pretend all that nonsense isn't there for a moment, or you could just call it u. And so the 5 drops down and the 5 goes to a 4. And so there it is. That's the straight up derivative of the outer function. And now the chain rule says, great, you did df du, but now you need to multiply this by the derivative of the argument. So I'm just going to write that out. We now need to multiply by the derivative of the argument. And so there is my complete math statement with the command in it saying that we still need to take this derivative here. So helpful to use this to show you step by step what's happening. So now, this is the derivative of the inner function, but because this has more than one chain rule in it, means we now have a new outer function and a new inner function. And the chain rule says, well, you got to take the derivative of the outer function first. So the outer function is sine, and what's the derivative of sine? Well, the derivative of sine is cosine. And that is just a straight up derivative. The derivative of sine is cosine. And a chain rule says, cool, you did the outer derivative, but you still need to do that inner one. And so I'm just going to write that out. We still need to do then the inner derivative there. And so again, there's my next step of work. And now let's look at this. The derivative of e to the 3x. Is that a straight up derivative? It's not, because of the 3 here. Remember, the straight up derivative is e to the x. The 3 is blocking that. So this is another chain rule. And the chain rule says, well, you first have to take the derivative of the outer function. The outer function here is e. The derivative of e is always itself. So the derivative of e to the 3x, that straight normal derivative, is e to the 3x. But the chain rule says, cool, you did the outer, you got to do that inner. And so now the inner function here is 3x. And there's our next line of work. And now finally, 3x. Does 3x have an inner function? No. Which means then there's no more chain rule. And we can just straight up do the derivative of 3x, which is 3. And this is our final answer. So how many chain rules did we do there? And another thing I like to say with the chain rules, I like to say it pops out. And I just want to, in case you hear me say this in the future, what I mean by that. So here's our answer. So what I mean is that this cosine right here, cosine e to 3x, this popped out from this. Because that's all we did. We took the derivative of sine and bang, we got cosine. This popped out from the chain rule. And so that was one chain rule. Going from sine to cosine is one chain rule. And then we had to take the derivative of this. Inner function, I should say here. And the derivative of e to 3x, that's straight up derivative. The derivative of e is itself. And so this e to 3x popped out from this one. That was our second chain rule. And then we got to e to the 3x, and we noticed this also has an inner function, which means we have to do another chain rule. And so the derivative of 3x is 3. This 3 popped out from this 3x. And that was our third chain rule. So here is an example of 3 chain rules. And for your homework, I think the hardest one is 4 chain rules. So at this point, I obviously have no idea what's going through your mind right now. I'm sure this is probably looking pretty overwhelming at the moment. We just did 3 chain rules. And again, I can't stress enough, this is going to take practice to get the hang of, but we haven't even incorporated the product or quotient rule yet. All of this stuff can combine together to get to be pretty complicated. And I can't stress enough, practice, 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 so that you can get this under your belt. So let's check out this example. This is a chain rule with a quotient. Now, how would you know that? Well, first off, let me get rid of this F. First off, you want to identify what you have. In the numerator, we have a power function going into a power function. And this is all divided by another power function and a constant. Now the division bar here, we have a function divided by a function. So that's how we know we have to use quotient here, because we have a function divided by a function. And then we will explicitly define what f and g are. So we're saying here that f is explicitly x squared minus 5x, and that's all raised to the 10th. And then we're explicitly stating g is 2x minus 5. And then once we explicitly define f and g, we then take their derivatives for the quotient rule. So let's do the derivative of f. Here's our chain rule. And remember, the chain rule says, first, just take the normal derivative, the derivative of the outer function. So in other words, we're just going to pretend for a moment all of this is u, and the derivative of u to the 10th is 10u to the 9th. But that's not really u there. It's really all that. And again, this is what I mean by just doing the straight up derivative. Just do the derivative right from the derivative patterns. And that's cool, because that's what df/du means. And then the chain rule says, okay, multiply that now by the derivative of the argument. And what's the argument? It's x squared minus 5x. That is the argument that's being put into the other power function. And then what is this derivative? I'm just going to put an equals here referring to this part right here. And well you'll see. So the derivative of x squared is 2x, and the derivative of minus 5x is minus 5. And so this is our derivative. And this is the derivative then of f. And again, I know this can get very complicated, but I want you to see the simplicity here. We just did a straight up derivative here. The 10 dropped down, and we subtracted 1 from the exponent. That's a straight up power pattern derivative. And then we looked at the argument, and we took the derivative. And that's our answer. And now we have our pieces for the quotient rule. So the quotient, we have, and why don't I just write this out real fast so you can see it? So that's the quotient rule. And so what is f prime? Well, that's what we figured out. That's what the chain rule is right there. So it's a pretty big mess. I'm just going to copy all that. So f prime is that entire mess right there. There it is. And then what is g? Well, g is 2x minus 5. And then moving along, minus f. What is f? Well, here's f. And that goes there. And then g prime. Whoops, I forgot to do g prime. G prime. The derivative of 2x minus 5 is 2. And so going back to our quotient rule, g prime is 2. And this is all divided by g squared. And what is g? It's 2x minus 5. And here is our answer. Look, it doesn't even fit on Word anymore. This is definitely where having a board in classroom is helpful. And the only way I'm going to change that. And at least we can get that to fit in there. And that's our answer. It's not cleaned up, which means trying to distribute, gather like terms, and seeing what divides out. So it's not cleaned up. That's an algebra step. You will need to clean these up for MyMathLab. MyMathLab will only accept simplified answers. However, for the test, because simplifying this could take another 10 minutes, depending on how complicated it is, for the test, I'm not interested in the simplified answer. For the test, I want to know, can you get to this point? Because once you can get to this point, you've done calculus, and then the rest is algebra. So let's try another one. What do we have here? We have a power function, x squared. We have the trig function, secant. And 1 over x is another power function. Remember, now this is the way the book has it written. But remember, 1 over x is x to the minus 1, which is a power function. So identify the functions you have. We have secant and 2 power functions. The next thing you want to identify is, are we multiplying functions together or dividing functions? Because if we're dividing functions, we have to use quotient. In this case, though, we're multiplying 2 functions together. We're multiplying x squared times this trig function. And when you're multiplying functions together, we have to use product then. Now, what else should you recognize here? Well, look at x squared. X squared is not a composite function. The argument is just x. However, if we look at the secant function, the secant function is a composite, and its inner function is x to the minus 1. So what does that mean? That means there's no chain rule on x squared, but there is a chain rule on secant, because secant has an inner function on it. So continuing on with the product rule, the first thing we would do would be explicitly define what f and g are. So we're explicitly stating here that f is x squared. Whoops. And we're saying g is secant. Whoops. That x is right next to the c, to be fair. And that is x to the minus 1. And so those are our explicit definitions. And now we need to take the derivative of them. So the derivative of f, that's just a straight up derivative pattern there. The derivative of x squared is 2x. And now the derivative of g is where our chain rule is. So the outer function is secant. And so again, the outer function, we just take that derivative normally. And what's the derivative of secant? It's secant tangent. This is the straight up derivative of secant. And then the chain rule says, cool, you did the straight up derivative, but you gotta multiply by the derivative of the argument. So here's our full correct math statement here. And let's do then this derivative. What is the derivative of x to the minus 1? Well, the minus drops down, and we subtract 1 from the exponent. So the derivative of x to the minus 1 is minus x to the minus 2. I'm going to put that in some parentheses there so I can drag it over here. And that is our derivative for g. Now that we have our pieces fg and f prime g prime, we can now plug this in then to the product rule. And let me just first write out what the product rule is. That is the product rule. And we're going to plug our information in. So what is f? F is x squared. What is g prime? Well, g prime was all this ugliness from the chain rule. So I'm just going to copy all that. That is g prime. There it is. And having a tough time showing everything at once here. And now we want to do f prime, so plus f prime. F prime is 2x. And then finally times g. G was our secant then. So here's g. And that's g. And let's see if this fits on Word. And it does. It just barely fits in there. And that's our answer. Now, is it cleaned up? It's not. That cleanup could take a good 5 to 10 minutes, depending on how complicated it is. But, you know, right off the bat, like this x squared will divide out this x to the minus 2. So those will divide out. And we could factor out a secant on that. You know what? Why don't I just do that? Since this one's not too bad. So x squared and x to the minus 2, those will divide out. And this minus sign, I'm just going to bring all the way to the front here so we can get rid of that. And each of these terms has a secant in common. And so we can factor that out. And to do that, I'm going to have to stick the minus right here. And that's our best cleaned up answer. There's nothing more we can do that's going to make that look any nicer. So let's check out one more. Sine of x squared times cosine 2x. What functions do you see here? Sine, power, cosine, power. So we will need those derivative patterns. Hopefully you can also see this is a function times a function. So we have the sine function times the cosine function. So that means product rule, multiplying two functions together. And what else can you see? You can see the argument of sine is not just x. So there's going to be a chain rule here. You can see the argument of cosine is not just x, which means there's another chain rule here. So this is going to be a two-chain rule product. And so once we identify it's a chain rule, a product, we then specifically define what f and g are. So we're saying f is sine of x squared, and we're saying g is cosine of 2x. Once we've explicitly stated what f and g are, we then need their derivatives for the product rule. And taking these derivatives now is where the chain rule kicks in. So, what's the outer function here? The outer function is sine. And so we just take that derivative normally. The derivative sine is cosine. And the chain rule says, cool, you did the normal derivative, but now you need to multiply by the derivative of the argument. And what's the derivative of x squared? It's 2x. And now, since x is just x, that means the chain rule is done. And, I'll say this, I'm hesitant, is why I'm hesitating. But technically, the chain rule is always happening. And what I mean by that is, technically, the next step I would say here from the chain rule is that we need to take the derivative of the argument. But the argument here now is just x. And a derivative of x with respect to x is 1. And that's what I mean by the chain rule ends. Once you get to just a single x, then there's no more chain rule, because the chain rule now will pop out ones. And so we're done. And that is our derivative for f. And I do want to say, now that I've said the chain rule is always happening, that is true. You should never question on whether there's a chain rule. There is always a chain rule. It's just that sometimes it pops out a 1. And so it doesn't look like it's doing anything, because it's not. Multiplying by 1 doesn't change anything. So I do want to stress, you should never question if there's a chain rule. There is always a chain rule. So let's check out this one, the derivative of g. The outer function here is cosine. And what's the derivative of cosine? It's minus sine. And so we did the straight derivative. We did derivative of cosines minus sine. And now the chain rule says, cool, but you got to take the derivative of the argument. And so the argument then is 2x. And what's the derivative of 2x? It's 2. And again, 2 has no argument, and so there's no derivative to take. And the chain rule is done. And that's our derivative. And now we'll put these pieces together. I'm just going to grab my, I didn't paste it in there. I'll have to rewrite it again. And then we're going to put that all into then the product rule. So just to write that out again so you know what the product rule is. There it is. And we're now going to stick our information in. So what is f? F is sine of x squared. So let's plug that in for f. There it is. G prime. G prime's got a minus sign in there, so I'm going to need a parentheses to make sure it doesn't look like subtraction. So there's G prime. Stick that in. Plus f prime. What is f prime? Here it is right here. And we'll stick that in. Here it is right here. We'll stick that in for f prime. And then finally g. G is cosine 2x. And we stick that in for g. And there is our final answer. And yes, it does need to be cleaned up. But that's all algebra at this point. This would continue. This would end the calculus. We finished the calculus, and now cleaning this up, simplifying it, would then be some algebra. So this is only our third lecture into test 2. But I want to say at this point, I really only have 2 more things to say for test 2. In other words, these 3 lectures is pretty much the bulk of test 2. And like I said, there's 2 more things I have to say in the upcoming lectures. It will all involve what we're doing here. And I just want to stress again, practice this skill. Practice these problems. That's why I have the practice homework. And don't forget, you can always do odd number problems in the book, because the odd number problems have the answer in the back of the book, so you can check your work. If you don't have the book, you can use the e-text to check those problems. And what's going to happen with test 2 is I like to present test 2 in increasing difficulty. And test 2, almost every question will be find the derivative. And I'm going to increasingly make derivatives harder and harder on test 2 to see how far you can go. So the easy questions will be, what are the derivative patterns? So an easy question on a test would be, what is the derivative of sine x? And I'm testing you then on those derivative patterns. And then I'll up the difficulty by adding in a derivative property. So the next difficulty would be then having functions that are added or subtracted. Can you distribute? And then I'll up the difficulty again by including a product or quotient. And then I'll up the difficulty again by adding in two products or two quotients. And then the difficulty gets upped even more by adding in the chain rule to all of that. And that's what's going to happen on test 2. It's going to be all derivatives. So I'm trying to let you know what's coming because ultimately I want all of you to pass. I want you to understand calculus because that's why you're taking this. And at this point, your primary goal is to get derivatives. Know the derivative patterns. Know how to use the product, quotient, and chain. And we aren't done. We will have more homework that will focus on putting all of these things together. And we will talk about that more in the next video.